Alright, today we're going to look at a type of equilibrium problem. This time we're going to deal with bases. Okay, so we spent the last time talking about finding the pH of bases, or acids. Now we're going to look at bases. Okay, so again, remember for most bases, this is just showing you some of the differences where, if this is water, you have hydroxide that's going to be floating around in hydrogen ion. This is most likely ammonia that's getting tossed in, that's going to go ahead and grab onto one of those hydrogen ions that got plucked off of water as well and left you with hydroxide. Okay, so again, it's kind of that two-step thing where we can think of different things that will influence the pH of a system. Now, strong bases, group 1A and group 2A hydroxides, we typically treat as our strong bases. For example, sodium hydroxide, calcium hydroxide, potassium hydroxide are really some of the most common ones. Now, if we had to find, say, the pH of a 5.0 times 10 to the negative second molar sodium hydroxide solution, exactly what we did earlier. Hydroxide is 5.0 times 10 to the negative second. And to find hydrogen ion, you could use the Kw expression. Okay, we know Kw is equal to 1.0 times 10 to the negative 14th, so we could solve for hydrogen ion of being 2.0 times 10 to the negative 13th, and then plugging that into the pH equation, which is 12.70. Okay, so that would be one way. Another way that you could have done, you could have gone right to pOH from here using the pOH equation and then subtracted it from 14. So there's a couple of different ways to do it. And the only thing to keep in mind, and this is where we get caught up here, is if it was a hydroxide solution. Okay, if it was a hydroxide solution, remember there are a calcium hydroxide solution. There are two hydroxides for every one calcium. So we would have had to come up here and multiply this by 2 in order for that to work. So we would have, instead of an initial 5.0 times 10 to the negative second, would have multiplied that by 2 because we would have had 2 hydroxides for every 1 mole of solution. Okay? Alright, now weak bases do not contain hydroxide, but it will accept hydrogen from water to make hydroxide. So that was where we had, usually has at least one unshared pair of electrons, and it uses that unshared pair to form a bond with hydrogen. That's why ammonia is such a really common weak base, because it has that extra lone pair. It goes ahead and it sucks away that hydrogen, and so you're still left with hydroxide, and that is what gives the solution a basic situation, so to speak. Okay, now we've done Kc, we've done K, which is equal to Kc, which is also Keq. We've also done Kp, which is our pressures. We did Ka with acids, and now we've got Kb with bases. We're getting there. But this refers to the reaction of a base with water to make its conjugate acid and hydroxide. And just like we had for strong and weak acids, we do this for weak bases only, because the strong bases completely dissociate, so we don't have a Kb value. This is the generic form. B is going to stand for base. You're going to react that base with water. Remember, the reaction that's going to take place is that hydrogen ion is going to attach itself. So you're left with the conjugate acid of the base as well as the hydroxide ion, which is also going to be the conjugate base of water, which is going to serve as the acid in this situation. Okay, so you still always need to think of them as those pairs. Now, this is going to pop up. Hopefully I didn't run out of space. Here is our generic Kb expression. Remember, we don't include water because it's a liquid. Okay, everything else goes in there. Sometimes you'll see me include it in the ice table, sometimes not. It just depends. Alright, so let's run through some solutions, and some of these you guys will have to write down, so you may need to fill in your notes. This is example 14.13 on page 680. You need to find the pH of a solution for 15 molar ammonia. Now, ammonia is a weak base, so you've got the Kb value of ammonia. Keep that in mind when you're doing your practice problems, because this one's a really common weak base. Ammonia will create more hydroxide than plain old water, because remember, when we're comparing Kb values, we compare it to Kw. Kw is 1.0 times 10 to the negative 14th, so it's less than water's contribution. Remember, a strong base, you're going to compare it to times 10 to the negative 7th, because we treat it as being neutral. Okay, so you want to plug these in. Notice I put the water in here, but there's nothing listed there. So the initial concentration for ammonia is 15, 0 for ammonium, 0 for hydroxide. We're going to have minus x plus x plus x. We've got our E, so it's plain old ice table. And then we're going to get to setting up our solving for our KB expression. We went ahead and did the assumption that it's going to work. We get an x value of 0.016. To check our assumption, we have to make sure that whatever that x value is at least 5%. 5% or less than what we're subtracting it from. So since it was 15, the initial concentration was 15, it's 0.11%. The 5% rule checks out. So now we can go ahead and find, remember the original question is what was the pH. So in order to do that, the only thing you got to keep in mind for bases is that typically that X value is the hydroxide value. I would say a safer bet, because with some of these strong solutions we can actually be off the charts. So sometimes it may be a safer bet to use the KW value in order to find the hydrogen ion concentration. But either one is really going to work. Then once we find hydrogen ion, we can plug it into the pH equation and we get 12.20. Although, if you go back to your original sig figs, they gave us 15.0. Typically we don't use the KB values to limit the number of significant figures, but it looks like that's what they did, and that's where they got the 2 sig figs from. So that's where that's going to come from. Which again makes sense, because if it's ammonia, it's a basic solution, it's greater than 7. Okay, another example. You have codeine, which is a weak organic base. Okay, 5.0 times 10 to the negative third molar solution of codeine has a pH of 9.95. We want to calculate the Kb, so we're going to work backwards. Okay, the chemical reaction. Now I know you may go, well, how the heck am I supposed to know what it is? Well, if it's a weak base, the chemistry that's still going to happen is that you're reacting it with water. Remember, it's going to take that hydrogen ion and it's going to grab onto it. So really all you got to do is put that hydrogen ion right out front. It's going to give the whole thing a 1 plus charge, and then you're going to be left with hydroxide. Okay, so even though it's new chemistry, it's not completely foreign. Now, to find hydroxide, we first can work backwards from the pH. pH is 14.00 minus 9.95, so we've got 4.05 for our pH value. And then we can work backwards to figure out the... No, I'm lying. That's our pOH, because they gave us pH up here. You can find the hydroxide by using the inverse log 10 to the x key of 8.9 times 10 to the negative fifth. Again, you could have used kW, different ways to do those. Now we got to go back to our ice table. So we've got our setup here. Remember, we've got water on here, but because it's a liquid, it's not included in the equilibrium expression. And we already found our x. Okay, remember, we just found out what the OH hydroxide value was. So now we can go ahead and we know our x value. So we can plug and chug. Remember, we don't ignore the x when we know what it is. Okay, so we're going to go ahead and plug it in, because you'll notice, I don't know if you just heard the bell there, you'll notice these aren't that far off, but the only time you can get rid of the x is when we're trying to solve for it. So our final answer should be 1.6 times 10 to the negative 6. Remember, capital K, no units. Okay, which we like. And the reason we have 2 sig figs is there were 2 decimal places in our pH value. So, plus our molarity was 2 sig figs. Okay, so let's talk about polyprotic acids. We've heard this term before. Polyprotic acids are acids that can donate more than one hydrogen ion. Okay, and they always dissociate one at a time. So you kind of have to think of them as steps, and this is why. So for example, carbonic acid, okay, H2CO3, step 1, the Ka is 4.3 times 10 to the negative 7th. Okay, and you'll notice it says Ka1. Step 2 is 5.6 times 10 to the negative 11th. So you have different Ka values, and you'll always notice this, that Ka1 is always going to be stronger for Ka than Ka2, than Ka3 for a typical weak polyprotic acid, and it just all has to do with the attraction. Okay, if it kicks out more hydrogen ion, it has to do with equilibrium. Well, if we just look at step 1 in isolation and you freeze frame it, there's already hydrogen ion floating around. So it's going to be a little, and all the, since it's a molecular compound, all the electrons and all the atoms are going to be sucked together a little bit stronger. So it's just going to take a little more energy. I don't know, that's kind of how the way I remember it. But so eventually, but Ka1 is larger than Ka2, than Ka3, etc., etc. Okay, so some polyproducts that are pretty important. Phosphoric, really only the first step creates an important amount of hydrogen ion. Sulfuric, the first step is a strong acid, the second step is a weak acid. These are really the most common polyprotics that we see. Remember, phosphoric is a weak acid to start with, so that's why only the first step really creates it. But we treat the hydrogen sulfate ion as a weak acid. Okay, so that's another reason where I haven't necessarily told you all the truth on these. And these are just ball and stick figures of those. All right, so now let's look at a situation where you have to find the pH value of a polyprotic mixture. And so the way this is going to work is that if I have the pH of 1.0 times 10 to the negative second molar, oops, shooting ahead there, molar sulfuric acid solution, and the first thing you got to figure out are we got to kind of go back to the major species. What's floating around, what's going to influence my pH value. My major species are going to be hydrogen ion, hydrogen sulfate ion, and water. Now, the first dissociation is a strong acid, so it's going to completely dissociate. So from step number 1, you'll notice we started with hydrogen sulfate, we automatically get 1.00 times 10 to the negative second molarity. So when we go ahead and we make our ice table, we can plug that in from the first step, so to speak. Now we still have our concentration of hydrogen sulfate ion, so that's when it's polyprotic. It's kind of like the mixtures. I always think of it as a mixture of a weak acid and a strong acid, just like we had to combine the hydrogen ion from step 1. So we've still got our setup here, 1.00 times 10 to the negative second, minus x's, plus x's for our reactants, etc. So now we got to solve, and this one, the oh, how do I know that I can't solve for it? Let me tell you. The reason I know I can't solve for it is that when I find Ka, okay, Ka is pretty small. Ka is 1.2 times 10 to the negative second, okay, and it wasn't given to you in the problem, but you can find it in the textbook. So that Ka value of hydrogen sulfate is going to be 1.2 times 10 to the negative second. Well, that's not 3 decimal places away, so I have to use the quadratic formula. Okay, I have no choice. You know, you guys can find different sources where it will show it to you, but I have to work it out, and it should be 4.5 times 10 to the negative third for the second dissociation of that second hydrogen ion. So now what I can do is, remember, to find the hydrogen ion, I have to add both of those together. So I'm going to take 1.4 times 10 to the negative second, which was from the first dissociation. 4.5 times 10 to the negative third from the second dissociation. I'm going to get 0.014 for my total. My pH value then is going to be 1.84. And again, I'm pretty sure the reason they're limiting it to sig figs is because of the Ka and the Kb values. Okay, so that's finding mixtures. There are also some more examples on page 683 on your textbook, but hopefully that helps with bases and polyprotic acids. And then we'll get to the last section. Okay, good luck.